So we're going to, in these slides, just state the mean value theorem. I'm not going to prove it. You can go to any mathematics textbook and see the proof. But the thing is that the mean value theorem is so logical. It's so easy to understand. It's not that complicated. It's very logical. So let's state what it is. If you take any function and you take 2 points on the function, we're going to call the function g of x. And if you make a line between these 2 points, and then if you calculate the slope of the line, now what's the slope of this line? Well, you take the value of the function g at x2, this distance, subtract from it the value of the function g at x1, this distance, and that will give you this part over here. And then we divide by this distance, x2 minus x1. So that's clearly what the slope is of this line. Okay, and now the mean value theorem says that we will always find a point C on the x-axis between x1 and x2 such that the derivative of the function g at that point, if you calculate the derivative of g at this point, the value of the derivative at that point, which represents the slope of the curve at that particular point, will equal to the slope of this line. And you can see it graphically. It's very clear to see graphically that if you take this line over here and you want to find the point on this curve where the slope is the same as the value of the slope of this line, clearly it's going to be this point somewhere around here. And so the mean value theorem just guarantees that you're always going to find this value c between x1 and x2 such that the derivative of the function g at that point has the same value, which means the slope of g at that point has the same value as the slope of this line. And why does this totally make sense? Because let's say if the function between the 2 points is just a straight line, then clearly all the points here have the same slope as the line joining the 2 points. Okay, well, if you make your function a little bit above the straight line, clearly there has to be some point somewhere where the slope at that point will be the same as the slope of this line. It just graphically it makes sense even. And what if the value of the function went below the straight line? Well, you'll clearly graphically again, you'll always find a point where the slope at that point is the same as the slope of this line. Now, I'm not doing a proof here. I'm just saying that it's very logical. It's not something unusual. It's not something that doesn't make sense logically. Okay, now where does this break down? It breaks down if you have, say, a function like this where there's a point that has no derivative. And so clearly if you look at this function, the green one, the slope of this straight line is not definitely the same as the slope of this line. It's not the same as the slope of this line. And this point has no derivative. And so we have to exclude such kinds of functions. And so we have to take only functions that are differentiable. And that means we can't have these kinds of points, these kink points here, right? Where the function changes slope dramatically. Okay, or other cases where this will break down is if you have, let's say this is the function, but then at the end point, the value is over here. So it's discontinuous at the end. Now clearly, if you make a line joining the first point and the last point, this is the slope of that line. And clearly this slope is negative. And you can clearly see also that on this curve, there's no point at all where the slope is negative. And so everything breaks down. So you have to just consider certain kinds of functions. The general then, the definition then of the theorem, or the way it's stated clearly, I mean very accurately, is that if g of x is continuous on the closed interval a and b and differentiable on the open interval a and b, then there exists a number c in the open interval a and b such that the derivative of the function at c has the same value, or in other words, the slope of the function at c has the same value as the slope of the line joining the endpoints a and b. So this theorem makes complete sense, and we're going to use this theorem to derive the fundamental theorem of calculus in the next video.